Welcome. In this session, we will look at derivatives of logarithmic functions. In the last chapter, we saw how to differentiate algebraic functions. There were two sets of ingredients. One was the general rules of differentiation, the product rule, quotient rule, chain rule, so on. Other one was derivative of a specific function, or rather specific set of functions, namely power functions. Now we want to expand that list by adding logarithms and the next section exponentials. If I want to do that, I have to go back to the definition, find the limit of the difference quotient. So let's start by looking at the difference quotient for log base a. So I take the value of the function at x minus the value of the function at x divided by h, and then eventually we'll do the limit. So I want to rewrite this expression so I can connect it to other limits. Logarithms have the property that difference of logarithms is logarithm of the quotient. So the numerator, log base a of x plus h minus log base a of x, is log base a of x plus h over x, and I will write divide by h as multiply by 1 over h. Then distribute the x in the denominator of x plus h over x. That gives me 1 over h log base a of 1 plus h over x. I can take 1 over h inside, and I will have log base a of 1 plus h over x to the power 1 over h. Now this should remind you of something we looked at numerically. Remember this limit, limit of as h goes to 0 of 1 plus h to the power 1 over h. So if x was 1, then we sort of know what the limit is, but what about general x? Now in that limit, the exponent was the reciprocal of this quantity, and this was the variable going to 0. So let's try putting that h over x as the variable and see what happens. If I put t equals h over x, then h is xt, so I can rewrite it as 1 over xt log base a of 1 plus t. I want only 1 over t in the exponent, so I'm going to split up 1 over xt as 1 over x times 1 over t, and just take the 1 over t inside the logarithm, where it becomes an exponent. So I get 1 over x log base a of the quantity 1 plus t to the power 1 over t. As h goes to 0, t goes to 0. Remember that the domain of logarithm consists of positive numbers, so x has to be positive, in particular non-zero. Now we know the limit of the expression inside the braces, that's e. So the whole expression goes to 1 over x times log base a of e. We will rewrite it in somewhat more familiar form by using change of base formula. Log base a of e is ln of e over ln of a, and ln of e is 1, so that gives me 1 over x ln a. In general, I have this extra factor ln a, which typically is irrational for familiar numbers like 10 or 2. But in the special case that a is e, since ln of e is 1, I just get 1 over x. So ln of x, in contrast to other bases, has a particularly nice form. Derivative of ln of x is 1 over x. I can combine this with the chain rule to get the most useful form of this rule. If u is a function of x, the derivative of ln of u with respect to x is 1 over u times du over dx. You differentiate for the outside function ln, which gives reciprocal of what's inside, multiplied by the derivative of the inside. Let's look at a couple of simple examples now. First, I'm going to find the derivative of ln of the quantity x squared plus 1. Differentiate for ln, which is on the outside. That gives me reciprocal of what's inside, multiplied by the derivative of the inside. The inside is x squared plus 1. Its derivative is 2x. Or more traditionally, we would write the answer as 2x over x squared plus 1. Note that this has a very simple pattern. If I differentiate ln of an expression, then I get the expression itself in the denominator that comes from differentiating for ln, then the numerator is derivative of the inside, so derivative of this denominator. If you remember this pattern, it's a very simple way of remembering the rule for differentiating logarithms. Of course, you can also have operations done outside logarithms. Then you use the chain rule essentially the same way. So let's differentiate the square of ln. By the way, this notation, ln and then the power and then some expression, means you first do ln, then do the exponent. So written in more familiar form, this is simply derivative of ln of x quantity squared. Now the outside operation is power 2, so I have to use the power rule, which gives me 2 times power 1 of what's inside the parenthesis. So it's 2 ln x. I must multiply it by the derivative of what's inside the parenthesis. Inside the parenthesis I have ln x. If I differentiate that, I get 1 over x. So I get 2 ln x over x. I will stop this session here. Next time we'll look at somewhat longer examples.